Now, let's consider an electrophilic aromatic substitution on an aromatic ring that already has a substituent. So that is toluene. And let's say there's a couple of things that we need to consider. One is, what is the reactivity of the substrate with respect to benzene? And then where is, they say, substituent going? Where it's going to be attacking ortho, meta, or para. So those two factors have to do with the nature of the group that is here. So now I'm going to draw another, I must say that I have here a methoxy group. So that is anisole. And now let's do here a halide. So chlorine. And now I'm going to add a different group. So this is nitrobenzene. If you remember when we were talking about the general mechanism, the electrophilic aromatic substitution happens with a nucleophilic attack from the ring through an electrophile to form your sigma complex. Therefore, this is your intermediate, one of the structures of the sigma complex. If this is your nucleophile, the more electron density we have here, the stronger the nucleophile. And that's where the groups go. Now, the stronger the nucleophile, so let's say more electron density at the ring, we have a stronger nucleophile to do that attack. The reaction is faster. When that is the case, we say that the group is activating. So that's the word, activating. So any group that will increase the electron density at the ring will make the nucleophile stronger, more powerful, and then the molecule would be more reactive than benzene, which has no substitution. So relative to benzene, which is the unsubstituted, what is the reactivity? That's the unsubstituted, only H's. So now, in the case of toluene, toluene reacts faster than benzene. If this is faster, so the metal group acts as an activating group. And so now, also anisole reacts faster. So we're going to say that is electron donating electron density to the ring. And that's easy to say, understand if we look at the resonance structures, for example, here, in which you can draw significant structures having all the atoms with octets complete, and you'll be placing negative charge on the ortho and para. And in other words, we are donating by resonance. You can see that you're donating electron density to the ring. In anything that has more electron density here, makes the nucleophile stronger. So reacts faster. Now, in the case, this too reacts faster than benzene, which is, say, your reference here, right? Your baseline. Now, these two molecules react slower than benzene. So we call this group deactivating. So these two alkyl groups in something with that oxygen, for example, these are activating groups. And again, that word means they react faster than benzene in electrophilic aromatic substitution reaction. These two molecules react slower than benzene, both chlorobenzene and nitrobenzene. So we say these groups are deactivating. You know, that's one thing, faster or slower. Then the other factor that we need to consider is where is the group going to be installed? So in the case of toluene, let's do toluene. And here I'm going to simply erase that. So where is the substituent going? All right, so let's say that I'm trying to nitrate toluene. So I'm doing nitric acid, sulfuric acid. So where is the nitric group going to go? Does it go here, here, or here? And notice that these are ortho position. These two are equivalent. And these two are equivalent, the meta position. And finally say that we have, I'm going to do a little square here, the pair position. So we have three products possible. We don't know yet, right? Ortho, meta, or para. Where is going? So for that, let's look. I'm going to use better, that probably easier to see if I use anisole. So I'm going to erase this too. And now, changing that to anisole. We said that by resonance, we can do that resonance structure, yes? So what we have here is electrons in the ortho position, and that is positive here. But I can continue doing resonance. I can put electrons here in another resonance structure. You will have double bond here, electrons here. Here's still your double bond, positive. That's your methyl group, pair of electrons. And yet you can do another resonance structure, placing the electrons there. And so let's throw it smaller here. So negative. And now I don't have this three resonance structure. What I'm showing with the resonance is that I have more electron density. So say in the hybrid, you will have that the ortho position is delta negative. The para position, they say in the resonance hybrid, delta negative, delta negative, delta negative. So I have these places that have more electron density. So then the nucleophilic attack will be from any of those places, ortho or para, to the electrophile. So activating groups in methyl group does the same thing, but not by resonance, but by hyperconjugation. So which is some overlap. And it's not, say, as powerful as the resonance effect, but nonetheless, activating. So when you have that possibility of donate electron density to the ring, you're making stronger the nucleophile, the ring. And as a conclusion here, these activating groups, we are activating. We're going to see, so alkyl groups are ethyl, methyl, we have OH, we have amino group, and we have, say, ethers, groups like that are activating. They can do that donation to the ring. And because of, you see that there is more electron density in the ortho and para positions, they are ortho para directing groups. What that is then is that in the reaction that I drew here, I have two main products. And now I'm going to draw it to the other side. So that's our conclusion, and we know why is that. Not only they react faster than benzene, but now that we know how they orient at the synthesis. So your products are going to be ortho or para to that group. So this is what you would be writing. So one product, say there's an ortho, so that is a nitro group. And the other products, I'm going to put a plus sign here, nitro. So ortho and para, nitro, anisole. These are. There are other considerations in regards of, say, if we want to predict how much of each of the products are in that case, here statistically, you have two ortho positions, the ones here in the pink, in one pair. So statistically speaking, you can predict to have more of the ortho product than of the natural. But some other considerations need to be done, particularly when we have large group here. When there is a steric hindrance, then the para product will be favorable. We'll be doing problems on that.